Hello, testing my volume. This video is unlisted right now. I haven't gone public yet. Okay, I am live now. So, hello everyone. I'm going to be studying discrete math again. Wait. Hold on. Let me just change to full screen. Okay, so last time I studied about logic and proofs. Like I completed this. And I'm going to be starting this chapter. So in the time of on of Königsberg in Persia, Prussia. How do you pronounce this? There was a river containing two islands. The islands were connected to the banks of the river by 7 bridges. 1, 2, 3, 4, 5, 6, 7. The bridges were very beautiful, and on the days off, townspeople would spend time walking over the bridges. As time passed, a question arose: was it possible to plan a walk so that you can cross each bridge once and once only, and only once? Euler was able to answer this question. Graph theory is a relatively new era of mathematics, first studied by the famous mathematician Leonhard Euler in 1735. Since then, it has blossomed into a powerful tool used in nearly every branch of science and is currently an active area of mathematics research. The problem above, known as the 7 bridges, I don't know how you pronounce this, is the problem that wait, the internet just cut off. Hold on, let me just check my video. So it's working fine right now. And the internet just cut out. So the problem above, known as the 7 bridges, is a problem that originally inspired graph theory. Consider a different problem below. Consider a different problem. Below is a drawing of 4 dots connected by some lines. Is it possible to trace over each line once and only once? So 1, 2, 3, and they're drawing like 2 cones. So let's try this. You have 1 dot, 2 dot, 3 dot, 4 dot. You have the hold on. You have this. Okay, let's see. So 1, 2, 3, 4. 1, 2, 1, 2, 1, 2. So what we could do, well, there are 3 edges here, 3 here. So we can start from here. Like do this. This is the middle. Do this. The end. Do this, this, this. and then this. Yeah, so we can make this shape and this graph by going over each line only once. I think when it comes to how you solve it is that each vertices, so this vertices is either like passing through. So I have a vertices over here, either with this vertices, either the line is passing through, either this is an intersection, either this is the starting area, or this is the ending area. So if this was an intersection, they're like even lines over here. So there's a line touching, there's a line touching, there's a line touching, and there's a line touching. If it's a starting area, there would be odd number of lines. So there's a line exiting, it would pass through, another line would maybe pass through. But the point is there are odd numbers. And same with the exit area. There may be lines passing through, but the point is it ends here. So with this shape, this one had odd number of edges. This one had odd number of edges. So that means two of the lines were like passing lines, and one of the line was either an entrance or exit. So that's why I started here, went here, and then went here, and then like that, that. So in my example, this was starting, and then this line was the ending line. If you have a graph, 1, 2, 3, 8. So we have 1, 2, 3, 1, 2, 3, 1, 2, 3. Can I connect these? Yeah. This is an edge, 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 and there are 4 vertices here. This is not possible to draw only once because there are 3 vertices with odd lines. One of them has to be an entrance, one of them has to be an exit, but you cannot have 3 of them. So this one is impossible to solve. Maybe you can have something like this over here. This corner has 1, 2, 3, 4. No, 1, 2, 3, 4. No, this is not an entrance or exit. This is not an entrance or exit. 1, 2, 3. This may be an entrance or exit. 1, 2, 3. This may be an entrance or exit. So you can solve this by doing something like this. Yeah, see? So I entered here, exited over here, and there may be other diagrams, other traces which can solve this. The point is there can only be 2 vertices with the odd number of edges. I think the only exception is that if there is an exit and entrance on the same vertices. So if you have a maybe something like this, you have an exit and entrance on the same vertices. So then every vertices has a even number of edges. So maybe like something like this. Vertices, vertices, vertices. All of them has even number of edges. Because the entrance and my internet just cut off again. Like the streaming just cut off. I don't know what the problem is. Uh, okay, so what I was saying, even number of edges. Either all edges has to be even or there has to be 2 vertices. There has to be 2 vertices with odd numbers. So one of them is exit, one of them is entrance, but you cannot have more than two. That's my understanding so far, but maybe they might say something different. There is an obvious connection between these two problems. Any path in the dotted line drawing corresponds exactly to a path over the bridges. Pictures like this dotted line drawing are called graphs. Although technically the picture above is a multigraph, graphs are made up of a collection of dots called vertices and the lines connecting those dots called edges. When two vertices are connected by an edge, we say they're adjacent. Oh, so these two vertices, this here and this here, are adjacent. The nice thing about looking at graphs instead of pictures of rivers, islands, and bridges is that we now have a mathematical object to study. We have distilled the important parts of the bridge picture for the problem. It does not matter how big the islands are, what the bridges are made out of. If the river contains alligators, all that matters is the land masses are connected to other land masses. To get a feel of graph and the types of questions we want to ask about them, let's explore four examples of graphs. This. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 2, 2, 2, 2, 2. 2, 3, 1, 2, 3. Okay. The graph G3, so this one, is presented as an adjacency list where each vertex gets a list of which other vertex it is adjacent to. The graph G4 is presented as an adjacency matrix where the rows and columns correspond to the vertices and the entries are 1 if the vertices are adjacent and 0 otherwise. The rows and columns are, oh, I see. So like A, B, C, D, E, F. This would be A, B, C, D, E, F. And then from top A, B, C, D, E, F. And then A is connected to, well, in this example, is connected to 3. And A, B, C, D, E, C, and E. Also, the row is the same. This would be, what do you call this graph? Where it's like same diagonally. So A is connected to C and E. And similarly for this. So it should be symmetric, this one. So you can use the row, either the row or the column to see which one are the adjacent vertices. Let's count the number of vertices and edges in each graph. Number of vertices in G1, 10, in G2, 6, G3, 1, 2, 3, 4, also 6, G4, 1, 2, 3, 4, also 6. Number of edges, oh my gosh. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So in G1 it's 14. 1, 2, 3, 4, 5, 6, 7. In G2 it's 7. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Hold on a minute. E connecting to C is the same as C connecting to E, right? So we only need to count half. 1, 2, 3, 4, 5, 6, 7. So there are 7 edges. Over here as well, we only need to count half. 1, 2, 3, 4, 5. And then these ones are repeated. Should have written it down. I want to see the answer. Vertices 10, 6, 6, 6. 10, 6, 6, 6. Edges. So 7 here. 5 here, 7, 5, 1, 2, 3, 4, 5, 6, 7, 7 here as well. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yeah, that's correct. Hold on, let me just check my YouTube. I don't know why my internet is randomly disconnected. So if a graph has 10 vertices, each with degree 4, how many edges? I was gonna say 40, but it's half of 40, right? 20. Before we start studying graphs, we need to agree upon what a graph is. While we almost always think of graphs as pictures, dots connected by lines, this is fairly ambiguous. Do the lines need to be straight? Doesn't matter how long the lines are or how the dots are how large the dots are. The way we avoid ambiguities in mathematics is to provide concrete and rigorous definitions. Crafting good definitions is not easy, but it is incredibly important. The definition is the agreed upon starting point from which all truths in mathematics proceed. Is there a graph with no edges? We have to look at the definition to see if this is possible. So a graph is an ordered pair G, V, E consisting of a non-empty set V called the vertices and a set E called the edges of two element subsets of V. Okay, let's see examples. Nowhere in the definition is they talk about dots or lines. From the definition, a graph could be A, B, C, D, E, and the edges are. So edges have two element subsets, right? Two element subsets of V. So AB is an edge, AC is an edge, BC is an edge, BD is an edge, CD is an edge. So it's not possible to have a graph with no vertices and no edges. Here we have a graph with 4 vertices and 5 edges. Looking at these sets and sets of two elements and sets of two element sets is difficult to process, which is why we often draw a representation of these sets. We put a dot down for each vertex and connect two dots with a line precisely when those two vertices are one of the two element subsets in our sets of edges. Thus, one way to draw the graph described above is this. So A, B, C, D. AB has a connection, AC has a connection, BC has a connection, BD, and CD. However, we could have also drawn the graph differently. For example, either of these. We should be careful about what it means for two graphs to be the same. Actually, given our definition, this is easy. Are the vertex set equal? Are the edges set equal? We know what it means for sets to be equal, and the graphs are nothing but a pair of two special sorts of sets. Are the graphs below equal? So we have an edge connecting A and C and B. So no, these are not equal. Consider the graphs. We have V1, ABC, V2, UVW, V1, ABAC, BC. We have UV, UW, VW. Are these graphs the same? These graphs are not equal. It is enough to notice that V1 is not equal to V2 since A is in V1 but A is not in V2. However, both of these graphs consist of three vertices with edges connecting every pair of vertices. We can draw them as follows. Clearly, we want to say these graphs are basically same. So while they are not equal, they will be isomorphic. You can rename the vertices of one graph and get the second graph as a result. Intuitively, graphs are isomorphic if they're basically the same, or better yet, if they're the same except for the name of the vertices. To make the concept of renaming vertices precise, we give the following definition. An isomorphism between two graphs is a bijection between the vertices of the graph such that AB is an edge in G1 if and only if f of A, f of B is an edge in G2. Two graphs are isomorphic if there is an isomorphism between them. In this case, we write G is isomorphic G2. I think that's how you read it. And isomorphism is simply a function which renames the vertices. It must be a bijection, so every vertex gets a new name. These newly named vertices must be connected by edges precisely when they were connected by edges with their old names. Right. Decide whether the graphs are equivalent or isomorphic. Maybe I say AD and CD. They are not equal because the edges are not the same. But are they isomorphic? It randomly disconnected again. I don't know why it did that. Uh, they might be isomorphic. We can try to build an isomorphism. We can say FA is equal to B, FB is equal to C, FC is equal to D, FD is equal to A. This is definitely a bijection, but to make sure that the function is an isomorphism, you must make sure it respects the edge relation. In G1, vertices A and B are connected by an edge. In G2, FA is equal to B. So A becomes B, B becomes C, C becomes D, and D becomes A. So AB over here would be BC, AC would be AD, AD would be BA, and CD would be DA, right? Hold on. There's no edge between B and D. Thus, F is not an isomorphism. Not all hope is lost, however, just because F is not an isomorphism, does not mean there is no isomorphism at all. We can try again. At this point, it might be helpful to draw the graphs to see how they should match up. A, C. So these are the edges, and these are the edges. So what we can do, we can keep A and C the same. But we can switch B and D, right? If we have one which is A, B, C, D. Hold on, let me just copy this. I can't copy it. Okay. I'll just type it in. B1, A, B, C, D, E1. What did they say? A, B, A, C, A, B, A, C, A, B, A, C, A, D, A, D, and then C, D. 2, 2, B, C, A, B, C, D, A, B, C, D, A, B, A, C, A, D, and then C, D. For this graph, A, B, D, E, A, B, A, C, C, D, and then B, C. So what we can do, uh, what we can do, if we switch B and D, that won't help. We switch A and C, maybe that might help. We switch A and C and A and B. What happens then? So let's say we have V3, where we have my internet disconnected again. They're like weird lag spikes. So anyways, so graph 3 is like graph 1, but I switched A and C, so and I switched D and B. So instead of A, B, I have C, D, A, C, C, A, A, D, C, B, C, D, A, B. So if I draw the third one, A, B, D, C, we have C, D, C, A, C, B, and then A, B. We have C, D, C, A. Yeah, we get this graph exactly right. And C, A, B. That means these two, if this graph looks exactly like this, If this and this is isomorphic, because I can create a bijection function to create this, and this are exactly the same, then if V2 and V3, if graph 2 and graph 3 are equal, and graph 1 and graph 3 are isomorphic, then graph 1 and graph 2 are isomorphic. Thus, G is an isomorphism, so G1 is isomorphic to G2. Sometimes people talk about graph with a special name like Kn or the Peterson graph, or perhaps raw graph without any labels. In this case, we are really referring to all graphs isomorphic to any copy to that of that particular graph. A collection of isomorphic graphs is often called an isomorphism class. There are other relationships between graphs that we care about other than equality and being isomorphic. For example, compare the following pair of graphs. These are definitely not isomorphic, but notice that the graph on the right looks like it might be part of the graph on the left. It doesn't look like that. So 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Actually, yeah, with this, this, and this vertices only, and the edges connecting them, you can get this graph. So this, this, and this. You would like to say the smaller graph is a subgraph of the larger. We could give a careful definition of this. In fact, there are two reasonable notions. We say that this is a subgraph of G, and right, G apostrophe is a subset of G, provided V apostrophe is a subset of V and E apostrophe is a subset of E. We say that G apostrophe is an induced subgraph of G, provided V apostrophe and every edge in E whose vertices are still in V apostrophe is also an edge in E apostrophe. Okay, I don't understand this definition. Notice that every induced subgraph is also an ordinary subgraph, but not conversely. Think of subgraph as a result of deleting some vertices and edges from a larger graph. For the subgraph to be an induced subgraph, we can still delete vertices, but now we can only delete those edges that included those deleted vertices. Okay, consider these graphs G1, G2, G3, G4. G2 is a subgraph. G3 is also a subgraph. G4 is also a subgraph. Here, both G2 and G3 are subgraphs of G1. They're also G4, right? But only G2 is an induced subgraph. Every edge in G1 that connects vertices in G2 is also an edge in G2. Every edge in G1 that connects vertices in G2 is also an edge in G1 in G2. In G3, the edge AB is in E1 but not in E3. AB is in E1 but not in E3. Oh, so in G2, all of these edges exist in G1. All the possible edges with the limited vertices exist in G1. It didn't take just the vertices, it took also the edges. G3 only took some of the edges. So what about G4 then? In G4, E is missing. F does not directly connect to C. F connects to E and then E connects to C. So this G4 is not a subgraph. G4 is not a subgraph even though it looks like all we did is remove vertex E. The reason is that E4 we have the edge CF, but this is not an element of E1. All right. Every induced subgraph is also an ordinary subgraph. Induced subgraph, so all the vertices are present and every edge whose vertices are still in V apostrophe is also an edge in V apostrophe. So a subgraph might not have all the edges for all of these vertices, but an induced subgraph has to have all of the edges, right? So that's what an induced subgraph is. G2 is an induced subgraph. G3 is a subgraph, but not an induced one. Back to some basic graph theory definitions. Notice that all the graphs we have drawn above have the property that no pair of vertices is connected more than once, and no vertices is connected to itself. Graphs like these are sometimes called simple, although we will just call them graphs. This is because our definition of a graph says that an edge from a two set element to from form a set of two element subsets of the vertices. Remember that it does not make sense to say that a set contains an element more than once. So no pair of vertices can be connected by an edge more than once. Also, since edge must be a set containing two vertices, we cannot have a single vertex connected to itself by an edge. That said, there are times we want to consider double edges and single edge loop. For example, the graph we drew for the bridges of Königsberg problem had double edges because there are two bridges connecting a particular island to the near shore. We call these objects multigraphs. This is a good name. A multiset is a set in which we are allowed to include a single element multiple times. I don't understand what a multigraph is. Um, there are times you want to consider double edges and single edge loops. For example, the graph we drew for bridges of Königsberg problem had double edges because there are two bridges connecting a particular island to the near shore. Can I see the graph for it? Oh, so this is a bridge. This is one vertex. This is one vertex. So from this to this, there are two edges. From this to this, there is one. From this to this, there is one. From this to this, there is one. And from this vertex to this vertex, there are two edges. Yeah, there are two edges over here. That's called a multigraph. A multiset is a set in which we are allowed to include a single element multiple times. The graphs above are also connected. You can get from any vertex to any other vertex by following some path of edges. A graph that is not connected. So a complete graph has all possible edges. That is, a graph is complete if every pair of vertices is connected by an edge. Since a graph is determined completely by which vertices are adjacent to which other vertices, there is only one complete graph with a given number of vertices. We can give these a special name. Kn is a complete graph on n vertices. Each vertex in Kn is adjacent to n minus 1 other vertices. We call the number of edges in a emanating from a given vertex the degree of that vertex. So every vertex in Kn has degree n minus 1. How many edges does Kn have? One might think the answer should be n times n minus 1. So every vertex in Kn has degree n minus 1. So n minus 1 edges. So how many edges in total? So there are n vertices. So n times n minus 1 divided by 2, right? Since we got n minus 1 edges n times, once for each vertex. However, each edge is incident to two vertices. So we counted every edge exactly twice. Thus, there are n times n minus 1 divided by 2 edges in Kn. Alternatively, there are n choose 2 edges. Since to draw an edge, we must choose 2 of the n vertices. In general, if we know the degrees of all vertices in a graph, we can find the number of edges. The sum of the degrees of all vertices will always be twice the number of edges. Since each edge adds to the degree of two vertices. Wait, what? So this has degree 3, this has degree 2, this has 2, this has 1. 3, 2, 2, 1. 3, 2, 2, 1, 8. That's twice of 4. Wait, hold on. So here we have an edge. So vertices, edges, I will create a tally. Actually, for the edges, I will create a tally. For the vertices, I will have it like this. A has, sorry, wait. Vertices. For the vertices, I will create a tally. For the edges, I will do something like this. A has one edge, right? The number of edges emanating out of A is 1. Number of B emanating out of, a number of edges emanating out of B is 1. I have 3, 3, 3 vertices. We are talking about complete graphs, right? We are only talking about complete graphs. 3, 3. C would have 1. C would give 2 edges. And that will add up to this and this. Then if I have D and 2, 3. Now we have 4. D has 3 edges and it adds up to this. That makes sense. A connects to all other vertices, B connects to all 3 vertices, C connects to all 3. So there would be n minus 1 over here. And there would be n over here. If you wanted to know, if we know the degrees of all vertices in a graph, let's do something different. Let's calculate the degrees instead. Degrees. A has 3. B has 3. Let's just delete this one. Delete this. So B has 2 now. A degree is 2. For C, degree is 1. 1 edge, 1, 2, 3 edge, 2 edge, 2 edge. Degree. Now what just happened? Degree is the number of edges emanating out of a vertices. And then the number of edges would be half of the degrees, right? Sum of the degrees of all vertices will always be twice the number of edges. I think now it makes sense to me. In any graph, the sum of the degrees of vertices in a graph is always twice the number of edges. The handshake lemma, sometimes called the degree sum formula. Lemma is a mathematical statement that is primarily of importance in that it is used to establish other results. Sometimes called the degree sum formula, can be written symbolically as, so the number of degrees is 2 times the edges. Here we are using the notation dv for the degree of the vertices v. One use for the lemma is to actually find the number of edges in a graph. To do this, you must be given the degree sequence for the graph. This is a list of every degree of every vertex in the graph, generally written in non-increasing order. How many vertices and edges must a graph have if its degree sequence is? So 2, 4, 4, 3, 3, 3, 2, 1. 1, 2, there. 1, 2, 3. So 4 vertices. 4 has a degree of 2. So edges would be like half of the degrees, right? 1, 2, 3, 4, 5, 6, 7. Wait, that doesn't make sense. How many vertices and edges must a graph have if the degree? You must be given a degree sequence for a graph. This is a list of every degree for every vertex. Oh, so degree for one vertex has degree 4. Sorry, wait. 2 vertices has degree 4. Wait. There are two vertices with degree 4. 1, 2, 3, 4. 1, 2, 3, 4. 3 with degree 3. 1, 2, 3. 1, 2, 3. 1, 1, 2, 3. 1 with 2 and 1 with 1. So the edges is like half of the sum of the degrees. So we sum them and the edges is 10. I think one possible way we can connect them is like this. At a recent math seminar, 9 mathematicians greeted each other by shaking hands. Is it possible that each mathematician shook hands with exactly 7 people at the seminar? Seven mathematicians, 9 mathematicians. So each mathematician would shake hands with 7 people. So there would be 7, no, degree of 7 for each mathematician, right? So 7 edges emanating out of each vertex. 7 edges emanating out of each mathematician. So 7 times 2 is 14. No, no, no. Exactly 7 people. So degree of 7. Degree of 7, 9 times. So that's 63, right? So I don't think this is possible. This would be twice the number of edges, resulting in a graph with 31.5 edges. That is impossible. We can generalize the previous example to get the following proposition. Proposition is a general statement in mathematics similar to a theorem, although generally of lesser importance. In any graph, the number of vertices with odd degree must be even. Wait, hold on. So we have so this has to be odd, right? This has to be even, right? So odd plus odd is even. Right. So if there is like a vertex with odd number of degrees, there has to be another vertex of odd number of degrees to like even it out, even the total sum. This cannot be right, right, I get it. Suppose there were a graph with odd number of vertices with odd degree, then the sum of the degrees in the graph would be odd, which would be impossible by the handshake lemma. We'll consider further applications of the handshake lemma in the exercises. One final definition. We say a graph is bipartite. The vertices can be divided into two sets A and B, with no two vertices in A adjacent, and no two vertices in B adjacent. The vertices in A can be adjacent to some or all of the vertices in B. If each vertex in A is adjacent to all vertices in B, then the graph is a complete bipartite graph and gets a special name, KMN, where number of vertices in A is M and number of vertices in B is N. Some graphs are used more than others and get special names. So Kn is the complete graph on n vertices, but a complete bipartite graph with sets of n, m, and n vertices. So 1, 2, 1, 2, 3. Wait. Is a bipartite if the vertices can be divided into two sets A and B with no two vertices in A. Okay. So for this graph, we can divide this vertices into one set and this vertices into one set because these vertices don't connect with each other and these vertices don't connect with each other. So we can put them into different categories. If each vertex in A adjacent to all vertices in B, then the graph is a complete bipartite graph. Okay, I see. So all of them in A connects to all of them in B. The cycle on n vertices is just one big loop. The path on n plus 1 vertices, so n edges, just one long path. 1, 2, 3, 4, 5, 6. So n over here is the number of edges, right? 1, 2, 3, 4, 5. N over here is the number of vertices. One is this Greek letter. Consider the graph. Wait, activate. Consider this graph. Okay. Each of the graphs below is isomorphic to this. So we have one lone edge, one lone vertex. Over here, there are two, so this is not isomorphic. This could be, this could be. If we switch E and F, get like, so wait, we have one lonely edge. We have one vertex with one edge. Every other vertex, so one vertex with one edge, one vertex with zero edges, and the rest have two. So over here, one vertex with no edge, one vertex with one edge, the rest has two. Over here, x has three, so it's only this one. Indicate the isomorphism by listing the vertices separated by commas in order they correspond to A, B, C, D, E, F respectively. So A is in the middle. 1, 2, then 1. 1, 2, then 1. Right, so we have U, and then B is the lonely one. That corresponds to X. C, that corresponds to Z. D, that corresponds to Y. We have E, that is between F and A. Hold on, this is confusing. E and F, right? We have E and F. This is U and V. No, wait. U is already done, which is V and W, right? V, W. Okay, you know what? I will end the stream here. I will continue studying about trees in the next stream. Okay, anyways, see you guys later then. Bye.